Swayam Prabha. Digital India. Educated India.
Okay, so let us conclude our discussion on instability on the attachment line of swept wing. We were talking about what other groups of people may have done. One specific instance was this work by Obrist and Schmidt in a couple of back to back paper in JFM. They investigated the flow fields of this kind, that if you have, let us say, a flow past a swept wing and this is your attachment line plane, and then what they did was probably, let us say, this is the edge of the shear layer. So, they took symmetrically positioned vortex on either side outside the shear layer, and then they allowed this vortex to move at a free stream speed. So, it is like this. So, this will perhaps go this way, that will go this way. So, these vortices that we may have may be a counterclockwise pair, but they would be moving at c equal to u infinity, or the oncoming flow here is given by u infinity. And what they reported was that there was not much of a growth rate inside the flow. So, this was kind of a different problem that what we discussed. We were discussing about a periodic vortex moving in this plane itself, and I kind of suggested that one could perhaps investigate what happens to a flow domain if we think of it as some kind of a natural barrier, and then we can construct a flow domain like this, and due to this inflow unsteadiness, what will happen for the three dimensional flow field. That would give us some fairly a decent idea what happens as a consequence of attachment line instability for the flow over the wing. And over the wing, then you are basically talking about both the mechanism being present. So, we are talking about if there is a streamwise instability, if there is a cross flow instability, or a combination of the two, everything should be picked up by a three dimensional direct simulation of such a flow. So, that was what was perhaps attempted in Obrist and Schmidt, but they did not see any effect of it. Probably they did not also study what happens in the attachment line. Maybe their attachment line flow was completely quiet. There was no unsteadiness in there. In contrast, what we have talked about, we talked about a bypass mechanism that showed how the flow became unsteady right on the attachment line plane itself. That bypass mechanism was once again explained in terms of disturbance energy equation. Just to recall what we have done about the disturbance energy equation, we start off with the rotational form of the Navier-Stokes equation, then take a divergence of it. That gives us the spatial distribution of this total mechanical energy E, which is given by this pressure plus the kinetic energy head. How it evolves in space is given by this, and this is what we are talking about, quoting from that paper by Sengupta and Dipankar. We noted in that paper that the disturbance energy equation arises by taking the divergence of the Navier-Stokes equation in rotational form. So, this is the total mechanical energy, and then what we did from here, we split the total energy, mechanical energy, into a mean part and a disturbance part. So, same way you can do the splitting for the velocity field also into a mean part plus a disturbance part, and the same way you could do the vorticity field also split into a mean part and a disturbance part. If we do this, then this equation represents this. So, that is the first part. What we are talking about, that rotational field of the Navier-Stokes equation as governed by the vorticity transport equation yields the Orson field equation. So, essentially this is the parent equation, this has everything in it, right. This is starting off from the full Navier-Stokes equation. So, if I talk about the velocity field there, like any vector, we should be able to show it as a composite of rotational plus irrotational part, and the vorticity transport equation is obtained by taking the curl of this Navier-Stokes equation. So, the way you can see the progenitor of Orson field equation is the rotational part of the Navier-Stokes equation, whereas this equation has both, because this comes directly from Navier-Stokes equation. However, what we have done, when we take the divergence of this equation to get this, we do get the irrotational part that contributes to it, right. So, that is what we are saying, that this equation is interesting, because on this side maybe what resides is the irrotational part of the field, and this side we can very clearly see the presence of the vorticity vector, as well as taking this cross product of velocity times the vorticity gives higher order rotational effects. Okay. So, although we are looking at the irrotational path, the origin, the forcing is by the rotational field. So, this is something that we must understand, and as this E is from the pressure head plus the kinetic energy head. So, one would be tempted to really hark back onto what Markovin might have suggested. Markovin sort of guessed that if you write out similarly a Poisson equation for the pressure alone, then you would also get similar such term. I could split it up, I could write it in terms of del square of P by Pd by rho, and then I could put all the terms on this side, and then one would talk about all this forcing etc. as some kind of a shear noise term. Okay. However, Markovin did not really go through this kind of steps to explain his point there. So, we understand that this Poisson equation that we have written for disturbance energy actually shows the coupling between rotational field of the flow field with the irrotational part. That is what I explained. This side shows you the irrotational part, this side shows you what is the origin from the rotational part. And this was also a very important point to note, that this mechanism of creation of disturbance energy does not depend on dimensionality. Whether we have a 2-dimensional flow or a 3-dimensional flow, this mechanism remains valid. This we will find out when we come to the next module of the course, where we talk about non-normal modes, spatio-temporal growth of disturbances. You will realize that for the last couple of decades, people have been talking about newer mechanisms of instabilities. Unfortunately, those kind of mechanisms are very much biased in favor of 3-dimensional flow field, and they do not work for 2-dimensional flow field. In contrast, what we have shown in discussing bypass transition in this part of the course is that we can see it in the flow visualization that the disturbance field is 2-dimensional, because we saw the dye filament were lifted up in its own plane. So, it remained two-dimensional, the mean flow. The disturbance field at onset was two-dimensional. Later on there was a lateral spreading. So, three-dimensionality would come in, but the beginning of the thing could be very much true for a two-dimensional flow field, right. That is was also explained in terms of our numerical results, which was based on 2D formulation, right. So, we can see this is rather a very more all encompassing scenario when we write down this disturbance energy equation. We noted that a significant unsteadiness with large spectral bandwidth disturbance can be created without the vortex stretching mechanism. See, this was also another thing that we have noted that for a long time the discussion in fully developed turbulent flow has remained with the writing of the vorticity transport equation for general flow field, and that vorticity transport equation looks like this. We have this term plus V dot del, the vorticity, and on this side we have the vortex stretching term, omega dot del. Okay. So, what happens is if we are talking about 2D, of course, this itself, this operator itself is 0 and it does not make sense. So, this vortex stretching term can only be present for three-dimensional flow field. And this was very elegantly used, this observation, the splitting of vorticity transport equation in this form was very elegantly used by Kolmogorov and his school, where they showed how energy cascades due to this nonlinear term from small value of wave number to large value of wave number, the energy cascades. We'll come back to that discussion in the second part of the course. However, if we are looking at two-dimensional flow field, we do not have this term at all. So, basically this over reliance of talking about the reason behind large spectral bandwidth due to vortex stretching is probably overemphasized, because we have shown in this part of the course that it is indeed in 2D flow we get it through the bypass mechanism. We shown how quickly, I mean, you get the spectrum full from the calculations also, 2D calculations. So, that should really be able to convince us that we could get small scales in transitional and turbulent flows via 2D mechanism itself. Okay. And of course, if we look back a little further, we have shown that there could be other mechanisms of creating any length scale via dispersion. If you recall, we did talk about those periodically passing vortices. When we talk about this periodically passing train of vortices, they excite a very large integral multiples of fundamental frequencies. For each frequency, we create a chosen k from the eigenvalue analysis. And so, when I have infinite number of such circular frequencies, I have corresponding wave numbers. So, we are talking about this over reliance on vortex stretching term is a little bit of a historic legacy at this point in time. It is time for people working in the field to realize that there are these two other potent mechanisms. One is, of course, the dispersion mechanism that we showed in term for the case of periodically passing vortices, and the other case is the bypass mechanism, where we obtain the similar picture bandwidth filling case for aperiodic vortex passing by. So, I think we should be able to understand what we have been talking about. Now, if I look at the attachment line instability once again, we have seen in the last class the effect of counterclockwise rotating vortex. What happens when we have clockwise rotating, convecting vortex in the free stream? This were also studied. You see almost the same thing that we studied for Blasey's boundary layer. So, whatever we saw there, it happens here too. And we also note that if we look at clockwise rotating vortex, ahead of it you are going to see a favorable pressure gradient. So, we should see that if we do the calculations, right. Now, when we look at clockwise rotating vortex case, we are going to see none of this secondary or tertiary instabilities that we saw for counterclockwise case, because there it was everything was triggered by adverse pressure gradient, and the cascade was accelerated because of this primary to give rise to secondary and tertiary. But here what happens, the scenario is completely different. Ahead of the vortex, for a clockwise rotating vortex, you are going to get a favorable pressure gradient. Even though you can create some kind of large disturbance, it is going to be attenuated due to favorable pressure, and there is no question of secondary or higher instabilities showing up there. So, this is something that we would like to see, that the disturbance growth is not promoted, and even if there is some, they would be attenuated very strongly ahead of it, and if there is something going to take place, that should be behind the vortex, right. So, that is what we see in this picture rather very clearly. Now, you can see what is happening. We are seeing the vortex. This is now outside the range. Here the vortex is somewhere here, and this lifting up is happening behind. So, you can reason out that the vortex must be here, and then you can also see just ahead of the vortex the boundary layer thins down. So, you can see the vortex must be exactly on top of this. So, that is why you do not need to even provide the arrow. And as it goes along, we have noted from that sketch, recall that flow past a rotating and spinning translating cylinder, we saw how the streamline converges and diverges. For this case, streamline diverges just behind the vortex, but again if you go a little further down, again streamlines are narrowed down. So, this adverse pressure gradient is very localized, very localized, and that is what causes a single vortex to be created. You are not going to see a large sequence of vortices. So, that is what you are seeing, that with time they just simply pass by and nothing much happens. Flow reverses back to its undisturbed condition, and that is what a good receptivity calculation should reveal. And all these things happen. The top frame is from at t equal to 804, the bottom frame is around t equal to 1400. So, in that period of time we see all these things happening. So, I have talked about the DNS of attachment line instability as they thought they were doing, but they were actually doing something else. So, now you understand, like well, the hope was that if I take these two pairs, then if there is something that is happening on the attachment line, that will be automatically picked up, because your computational domain included both the top surface as well as the bottom surface, but unfortunately they did not pick it up. That is due to the wrong choice of the convection speed of the vortex. So, that is one thing we can say. Various other people have performed direct numerical simulation. When full Navier-Stokes equation is solved to reproduce experimentally observed leading edge contamination effects, there were many researchers providing some different versions of their own results. That is something that we just simply briefly discuss, because it is important that not only you should have a powerful computational tool, you should also have the physical understanding of what you are computing. For example, Spalart did a 3D DNS. He could not even produce the equilibrium flow itself, and that was experimentally reported by Hall and Malik in 86. So, what was wrong? But it did produce the so-called transitional Reynolds number from the experiment of Paul. So, this is really comes with a exclamation mark, because if you cannot even get the equilibrium flow, but you do get the disturbance flow, then well, it could be a coincidence. Okay, why we should not repeat what Spalart did was Spalart actually used white noise to trigger instability, and we have seen our explanation here shows that it is a vortex induced instability. So, we have to create a vortical disturbance. If that coherent vortical disturbance is never going to be represented by a white noise, that is one thing. And then of course, this kind of artificial constraint dictated by the computational constraint. He took a finite span-wise domain and then they said flow is periodic in that direction. Although I do not think this is a major issue as such, because our calculations were done for 2 dimensions. So, you do not really need to worry about the 3 dimensionality of the flow. In addition, there was a buffered domain that was used in the chordwise direction. So, basically if one is solving like this, so there is a buffer layer at the outflow. That was what was done by Spalart, but unfortunately, I mean, it was not too successful. 2-dimensional DNS were performed by Theophilus, who predicted wrong frequency of disturbances as compared to the experimental value of Paul et al. While Spalart's physical model was somewhat flawed, my understanding is Theophilus's failure was totally due to wrong numerics and not posing the right problem. In contrast, Jocelyn did some work in NASA Langley. He did not use any span-wise periodicity assumption and could get to show the existence of subcritical 2D equilibrium solution of Malik and Hall. So, that was shown. Subsequently, Jocelyn went ahead and computed 3D flows as well, and was quite eminently successful in showing this bypass transition in a computational framework. Okay, so thus it appears that all the simulations suffered due to various reasons. The primary ones, of course, is the inappropriate modeling of the problem through the boundary condition. For example, look at the failure of Spalart, who could not even capture the mean flow, or inappropriate excitation field, as it was the case in Obrist and Smid. They did not take the correct propagation speed. So, of course, the boundary conditions or the excitation field was not appropriate. It was going at the wrong speed. These are the 2 reasons that we should be attributing to the failure of these authors. Okay. So, finally, I think we would like to comment upon it. I just made a comment that Theophilus's results are wrong. That is probably due to this reason that we have to understand that when we are computing transitional flows, we have to have method which really satisfies dispersion relation, because that is everything. If I take a numerical method, the numerical method's dispersion relation is totally different from physical dispersion relation, that will not make any sense. And unfortunately, this concept itself was not existing in late 80s very much. Computationally, that you have to develop a dispersion relation preserving numerical method came into existence with those famous paper by Tam and Webb in 93 and 94. So, later on, of course, lots of people became aware, and we also developed a series of DRP schemes. We specifically zoomed into the parameter space where we should reside to attain this DRP scheme. This is something that we must do. What happens with spectral method? Spectral method is probably the gold standard of computing, because it just provides you the exact physical dispersion relation, provided you do let us say Fourier spectral method. Unfortunately, though, with such spectral methods, what you have to be worried about is the following, that you have to take some kind of a periodicity, and the spacing of the grid points either are uniform or given due to some various polynomials like Chebyshev polynomial dictating where the point is going to be. So, you could probably use that kind of information to stretching of points in defining the equilibrium flow, but once the disturbance say are created, you are going to create some of this coherent vortices. I could have a sort of a stretching like this. Let us say in the one normal direction, we may have this kind of spacing. As we are going away, we are stretching. So, now when I am creating a small vortex here, well, maybe this thing is quite adequate. So, I have this vortex, but then later on it is going to move like this. I may not have a complete control in computing such an event where the grid spacing is very sparse, and this does happen because this point distributions are a priori imposed by the roots of this Chebyshev polynomial. Whereas, if you work with non-spectral method, there is a possibility that you could choose more general grid point distributions, and that is something that we should be aware of. Okay. Now, this is where we come to an end to this discussion. We are going to now start off with a new topic, as I promised to you today itself, that we are going to talk about various other complementary efforts. Look, I mean, let us take a stock of the situation. Initially, we started off with Rayleigh's criteria of inviscid mechanism. Then came the viscous mechanism through Orr-Sommerfeld equation, and we found TS waves, right? That was created by viscous instability mechanism for external flows. Now, the classical approach that one follows is basically you first identify an equilibrium state, and then you study its stability with the help of a linearized governing equation. Now, if I do some very well designed controlled lab experiment, I can see they actually match quite well, and this is especially true when you see when this forcing is due to thermal forcing, like Rayleigh-Bénard problem, or some kind of a centrifugal instability that we could have, let us say, in a Taylor-Couette flow type of scenario. Those results match the lab experiments, theoretical and computational, theoretical and experimental results match very satisfactorily. But if you look at the general scenario where instability is predominantly dictated by shear force, there we fail by a great deal. The classic example is the Couette flow or the Posai flow, the pi flow. And we find that both these flows are unconditionally stable. But of course, we know such flows do become unstable. So, there is something wrong in that approach that linear stability fails to pick up. For example, quiet flow has been shown in a computational exercise to suffer transition at a Reynolds number of 350, but linear theory says it would not be unstable at all. Whereas pi flow, we know that the threshold limit is around 2000, and if you have it the Reynolds number above this, we can get this. And exact value, of course, depends on the facilities, the background disturbances, all kinds of things. If you look at the flow inside a plane channel, like what is called as a plane Poisson flow, the linear stability theory gives a critical value based on displacement thickness of the order of 5,700. Whereas this lab experiment reported by Davies and White in this Royal Society paper in 1928, they clearly established that you could actually have even transition as low as 1000. So, if this is something, please note that we have been talking about the Orson-Field equation solution and its ability to explain the instability in external flow was validated by Schubar and Skramstad experiment. But according to Trefethan and his colleague, even this analysis, eigenvalue analysis, is not always successful. I mean, provided we do a very tailor-made theoretical calculations and the corresponding experiment, like in Schubar-Skramstad experiment, we can show one-to-one correspondence. But for the same wall-bounded flow, for many other situations, your linear theory does not work. You recall we discussed about Klebanov mode. You recall that at low frequency, just simply do not have anything. So, there are this thing. So, that is why the Trefethan and colleagues do write that eigenvalue analysis actually fails even for the Blasius boundary layer flow. So, we should be humble enough to know where it works and where it does not. One of the features of traditional eigenvalue analysis is that the disturbance field is assumed to grow either in space or in time. This is entirely a failure of the method, because physically how do we know a priori whether the disturbances are growing in space or in time, or who knows, it can grow both in space and time. And that is what the title of this topic is, that we are trying to look for cases where we are going to see simultaneous growth in space and time. Those will be called the spatiotemporal instability, and they can also lead to transition. Okay? That is what we note, that this distinction between spatial and temporal instability is only for the ease of analysis, and there are really no general proofs or guidelines those available that would tell which method to really follow. Now, some work has been done trying to identify which method to choose, whether one should take a spatial method or a temporal method. A prime example is this review paper by Were and Monkiewicz. They actually claim to have applied combined spatiotemporal theory to flows in a mixing layer. Okay. They are basically interested in they were interested in finding out a criteria by which a flow can be analyzed using either the spatial or the temporal theory. And what they do is they inspected the dispersion relation in complex wave number frequency plane. You recall what we do in spatial theory, we take omega naught and complex alpha. That is your spatial theory. And temporal theory, you will take complex omega and real wave number. So what these people did were in Monkowitz, they just simply looked at the complex wave number and complex frequency. If you look at in this plane and then try to discern yourself which method would be more appropriate. So we need to understand that this methodology is trying to identify whether to take either spatial or temporal. This method does not talk about doing spatio-temporal analysis per se, right? So we must understand that that is somewhat limited in its application. But if you recall what we talked about, that Bromwich contour integral method, where we did perform the Bromwich contour integral going from along the complex alpha and complex omega plane parallel to the real axis. There we did see that we can work out a spatio-temporal behavior. And what we discussed so far for that part of the discussion, we found out that if we are looking at unstable cases, the results that we get by this complete spatio-temporal approach and the results that we get from spatial approach coincide. That was the result that we obtained in 1994, and we kind of provided a certificate that for that class of flow, spatial theory is adequate. But in this part of the course, we are going to revisit it once again and see what happens. So you see, basically in fluid flow, what we have will come across instances where you would see the disturbances are growing both in space and time. So it's quite natural that we will have to abandon those strictly spatial or strictly temporal analysis. And in addition to that, we have also noticed that if we create some kind of a three-dimensional disturbances like localized roughness, a dimple kind of a thing, which need not necessarily move like in Klebanov experiment. You can just simply have a physically a roughness, a rivet on an aircraft wing. That itself can lead to a flow in the wake of that roughness. A wedge, a turbulent wedge will be created. You don't see any Tolman-Schlichting wave in there. Wow, Tolman-Schlichting wave seeing is what? If you recall the Schubaum-Kramstad experiment, they did excite the system with a single monochromatic frequency, right? Single frequency. So, a monochromatic disturbance field. But if I put a sort of a rivet on an aircraft wing, then what is the frequency? Say I am having say free stream turbulence coming, that has embedded in it a kind of a frequency spectrum, not a single frequency. So, as a result, what I am going to get for each frequency, I am going to get a wave number if my dispersion relation is correct. However, the total response field will be sum of all these individual components, and that is where in a really a practical case in a natural setting, expecting to observe TS wave is a bit of an over expectations. We are not going to see a scenario where in natural case you will get just a single frequency excitation. That must be very specially designed. For example, if I talk about, let us say, the flow inside turbo machine, then what happens? You have the stator, rotor, etc. So, the stator will sort of eject vortices in its wake, and that will be impinging on the rotor, and that is where we saw that Kendall's experiment, where he rotated those two cylinders at the end of a pivot and then rotated it, and then those were ejecting vortices at a fixed frequency, and there you could see something, a signature of a TS wave like scenario. So, what do you see there? You saw there a TS wave packets, but in general you do not expect that. Now, there is a lot of activity that goes on in some of the Scandinavian countries, and a large number of them, they have actually focused upon what was called by Markovin as bypass mechanism. So, there are a large group of people who try to do. So, Brewer and Qureshi in their 1993 paper say that whenever you see such things where you do not see a TS wave, let us call them as bypass mechanisms. Okay. So, essentially even this spatiotemporal event people have tried to talk about as a bypass transition. What people have tried to basically follow in those approaches was basically they looked at the kinetic energy of the flow field and see how this kinetic energy changes with time. And if you see a large initial growth, transient initial growth, that is what prompted them to call those kind of phenomena as bypass transition. So, this is not a sustained phenomena. This is just a transient energy growth of kinetic energy. And I must point out that this kinetic energy is completely different than what we are looking here. This is the total mechanical energy, whereas those studies involve studying this kinetic energy. We will see what each of it leads to. It is noted that if you have such transient kinetic energy growth, it somehow works for three-dimensional flow field. Because if you do the corresponding analysis for two-dimensional flow, the growth rates even at the early times are very, very small. These are orders of magnitude smaller. Okay? This has been very clearly pointed out by Trefethan et al. In that 1993 paper in Science. They just do talk about it that this so-called transient kinetic energy growth is probably a probable mechanism for three-dimensional flow field, but not necessarily two-dimensional flow field. In the context actually this work of this so-called bypass transition following original idea of Markovin was by Landau. Landau did lots of studies starting from this 1975 paper. What he did show that you could see a 3D disturbance that grows algebraically. See now, if we look at the growth via Orson-Field equation, the growth there was exponential, right? E to the power alpha x minus alpha x or e to the power omega I t. So, those are exponential growth. But Landau just did show that if you sort of subject the equilibrium flow to some constraint, then you could get a three-dimensional growth algebraically. Now, you understand that there is a distinction between algebraic and exponential growth, because if I let us say plot time along this, then what happens? Say initially my let us say background disturbances are rather small and this is growing exponentially, we will not see like this. It will slowly pick up. Once it picks up some threshold amplitude, then it grows like this. Whereas, if you have an algebraic growth, then what happens? Then it could just simply go like this. Say suppose it is like a linear growth. I am not even talking about quadratic or anything. That could be significantly faster than exponential growth. So, Landau was basically probing with the idea that you could have in the initial phase you could have a algebraic growth, and that could take your disturbance to a significantly higher level. For example, here the distinction between the two could be 1000-fold or 10,000-folds, right? Whereas, at a later time, of course, if this persists and this goes, this overstrips. Okay? So, this is something that was proposed by Landau, and what he said that this is not related to Orson-Field equation, this is related to tilting of the vorticity vector by the mean flow itself. So, this is sort of a lifting mechanism of the vorticity field. Now, does it not ring a bell? What we did with vortex-induced instability, we are trying to lift the shear layer, right? So, we did see some such thing already in action. In later work, Henningsen, probably from the same school, as well as Brewer and Haritonides, they revealed that the algebraic instability is possible if you conceive of a coupling of modes between the solutions obtained via solution of Orson-Field equation and a square equation. Now, what is a square equation? This square equation is nothing but the linearized vorticity transport equation for the vertical component of the vorticity. You know, Orson-Field equation itself is an equation for the vorticity, linearized vorticity transport equation. But if you look at the vertical velocity component, then vertical component of vorticity, then the corresponding equation is called the square equation. So, you may have a Orson-Field mode in the xy plane, and then you can look at the vorticity in the y direction, right? Because if I have a flow in the xy plane, the vorticity is already in the z plane. So, that is your Orson-Field mode. So, Orson-Field mode will be in the z plane, but we are talking about omega y. So, the flow is in the x direction, wall normal direction I will have. So, that is your governing equation given by square equation. So, we can write it down, because we have written down the linearized vorticity transport equation. We can simply write the omega y component. This coupling of Orson-Field and square mode creates an inclined shear layer, which intensifies with time. Later on, Brewer and Landau collaborated and investigated the corresponding nonlinear growth. All those Orson-Field mode as well as square mode, we are talking about the linearized equation. So, they extended the study to include nonlinear growth, and that indicated that there is a possibility that you could get a secondary instability which can directly take the flow to a turbulent state. In a subsequent direct numerical simulation by Henningsen, Lundblad and Johnson, they again reported some bypass transition through a completely different breakdown mechanism. Well, what do we conclude from this? Either there are too many competing mechanisms, or multiplicity of theories may show limitation of each of them. So, we need to really focus our attention. Why people are interested in algebraic growth? That is what I was trying to show to you. This was explained in Brewer and Qureshi's paper. Firstly, the transient energy growth can occur for linearly stable system by 2 to 3 orders of magnitude, after which directly nonlinear effect can take over. Okay. Suppose my nonlinear threshold is here. So, then you can see for the initial algebraic growth, I have to go up to this time, whereas if I had depended upon exponential growth, I had to depend up to that long a time. So, whether I wait for this time or I have to wait up to that time depends on whether the algebraic growth is present or not. So, they are saying that if you have algebraic growth, then the nonlinear threshold can be reached earlier in the initial stages by such a mechanism. And when that does happen, you talk about it as a subcritical route, quite obviously, because you know, we have talked about the criticality with respect to the creation of unstable waves per se, but here this is somewhat of a different case, that I could have a flow where this is my RE critical based on OSE, right. So this corresponds to Orson-Field equation. And this people are talking about, let me clean up this diagram and explain to you what we are talking about. So if I am talking about, say, x or t along this axis, which we can talk about. So if this is my Re critical corresponding to Orson-Field equation, then if my algebraic growth starts taking off from early on, then that could be a subcritical thing. So this is your algebraic growth. Well, I could have different type of algebraic growth. I could have this kind of growth, I could have milder growth, and so on and so forth. What happens with the OS mode? OS mode picks up from here. Up to here it does not exist. So it picks up from here and then it goes like this. So what happens is, that's what Brewer and Qureshi is saying, that either it could be a subcritical route, or you could have a transient energy growth in a supercritical flow. So you come up to with the linear growth, then it switches on to the OS mode and then it suffers an exponential growth. So that's what is the second route that's suggesting that it could happen, that you could have initially an algebraic growth followed by exponential growth of during the supercritical stage. Okay. See, these are all very conjectural. These are all very conjectural. They are not been verified experimentally by controlled experiment in an unambiguous manner. So, however, there is an alternative viewpoint that treats the transient growth as due to non-normal modes. Now, what kind of an animal is it, non-normal modes? This has been pursued by Smith and Henningsen, who note that if you look at the solution of the Orson-Field equation or take the adjoint of the Orson-Field equation and the modes that you get, they are themselves orthogonal to each other. However, the Orson-Field eigenfunctions themselves are not orthogonal to each other. It is easily shown. If that is indeed the case, then what happens? Non-normality of modes of a fluid dynamical system are very hypersensitive to background disturbances. So if that is so, then what happens is, theoretically you are getting some kind of a eigenvalues, etc., but they are so susceptible to background disturbances that you can get some kind of a spectacular growth in the presence of disturbance itself. And this has been demonstrated for channel flow, that you have for channel flow, unlike that the case of linear theory, where we saw that critical Reynolds number was 5772, but we know experimentally it can trigger at much lower case. There it could be that the flow is not so-called uniform flow, it is coming with disturbance. Those are hypersensitive to disturbances. That kind of flow has been reported in Smith and Henningsen's monograph on this flow. I think I'll stop here. We'll pick up our discussion from this point onward in the next class, and we'll see what is the state of art in this particular area.